So I'm here again in Cannes at Thales Alenia Space with Thomas Walloschek, who is the ESA program manager for an exciting new mission called PLATO, which is going to be launched next, I believe, December. That's the target date. Not next December, but actually December of 2026. And we have just been visiting the clean room where part of the spacecraft is actually being assembled. It's not going to actually end up being assembled completely here. That will happen in Munich. And then it'll eventually see launch from an Ariane 6 rocket from Kourou in Latin America, South America. Target date again, December. So this is an unusual mission because you have 26 different cameras on one spacecraft, Thomas. How difficult was this mission from a technical standpoint?
It was, let's say, quite difficult and challenging to, let's say, get all the elements together and make it work together. So you mentioned the 26 cameras, but of course, this is, let's say, one part. So in principle, the mission is consisting of let's say 3 to 4 major elements. The first one is, of course, our scientific payload, which is the 26 cameras and also the electronic units on the one hand. And this is, as you mentioned, 26 of them, which is a mini-series production, which really was quite challenging in the past to set it up properly, because in the mission, this is done via a so-called multilateral agreement between a PLATO mission consortium, which is roughly 100 different members, institutes and industries working together to bring the cameras and the electronic units together. So here, for small series production, what was important was to have not only a super high quality, but super high quality for a very long duration, meaning 1 to more or less 2 years of constantly integrating the different units and the different parts of the cameras and manufacturing them. And for this, we built up several test facilities to make the final testing, 3 of them overall to be redundant, to be able to have to push through, but also several assembly lines on lower levels for the subsystems and the camera integrations and so on. So this is one big challenge. Then, of course, we have the industrial consortium with the PLATO core team consisting of the OHB Prime and together with Thales Alenia in Cannes and Beyond Gravity in Switzerland. And I would say from a platform point of view, we have parts of, let's say, known elements where we have attitude orbital control system and these kind of things. But we need to be a bit better than the normal attitude orbital control, and this is where we have, again, from the payload side, 2 so-called fast cameras, which are kind of fine guidance sensors, which are in the loop with the AOCS system. So really, here also the payload plays an integral part of the overall satellite to make it work.
And this is going to be, the field of view is something like 10,000 times of a full moon. Is that right?
Yeah, correct. Seen from the Earth.
As seen from the Earth.
Exactly, yeah.
And you have 24 cameras, which are scientific cameras, mm-hmm. and 2 cameras which act as fine guidance systems to give you the kind of navigational support, because you have to rotate the spacecraft, I believe, every 3 months to avoid the sun.
Correct.
From the Lagrangian point 2.
Yep.
Which is a prime location for such space missions now. It's a wide orbit, I think 1.5 million kilometer orbit, but PLATO will already have company to some extent. That's where the James Webb is stationed.
Correct.
Okay, so nominal mission of 4 years would hopefully be extended to 2 more years for 6, and then potentially 2 more years for 8. Mm-hmm. So. And the prime goal is to, unlike some previous planetary transit missions, tell us what a planetary transit is and why PLATO will be different. PLATO, the prime goal is to find an Earth-like Earth 2.0.
Yeah.
So tell us how PLATO is different from previous planet hunting missions using the transit method.
Yeah. So first of all, the transit method, easily explained, is you have a light source and then you move something in front of the light source. When you look at the light source, the light intensity, if an object goes in front, will decrease, will have a ditch, so to say, and this is what we are trying to observe. So we are trying to observe elements, planets, moving around stars, looking at a large field of view where we can observe many, many stars at the same time. We look at these, at the fields for 2 years. As you mentioned, we have to rotate, which is also quite from an, let's say, operational point of view, where we have another partner there, which is ESA, the ground control for the operations. They need to take care that we are always pointing then in the right direction and that the sun doesn't touch the telescopes themselves. So,
but basically you're looking for the dimming caused by an
Exactly.
Earth mass or Earth-sized planet in front, as it moves
In front of stars.
periodically in front of its parent
Exactly.
star, which is a very difficult
Yeah.
observation to make, and it takes a lot of precision. But you will you'll be looking at 100,000 stars at least per field of view, and you potentially could find Earth-like planets circling each of these individual stars without ever retargeting the telescope, the spacecraft. That's pretty amazing. Is that correct?
Yeah, absolutely. I mean, this is the point. You have to point at the same spot more or less for 2 years, because if we are talking about Earth-like planets around Sun-like stars in the habitable zone, we know roughly, probably it takes a year for the planet, let's say as an example, to travel around the star. And we want, as a confirmation, to have at least 2 transits in front of the star to be sure that we have really detected a planet and nothing else. And here also it's important that we will define, let's say, Earth radii, mass, and so the bulk properties there, which will help us to make a big catalog of potential exoplanets, which we then can use again for other missions to look there in detail, to do additional science and so on. We also have ground-based observations where we identify some targets where we can then also get some additional information. And in addition, we also do astroseismology, where we are trying to find out more about the host star of this planet, because this will tell us a lot about, let's say, how the system was building up and how it's evolving.
So Thomas, thank you so much for your time today. Thank you for your expertise and sharing your knowledge of this mission. We look forward to following it in the months and years ahead.
Thank you.